minus k in multiplication at z for z prime?
Minus k.
Because we are like derivating it.
So there is -1 here. So this is x power minus k. So I am subtracting 1 from this.
Sir, yes, so subtracting the power, but shouldn't you also multiply this whole term with minus k?
So
Yeah,
derivation.
yeah, yes, sure, sure. Yeah, you're right. Yeah, I had to multiply with minus k. You're right, correct. So it should be minus k. Right? This is correct now, right?
Yes, sir.
Yes, sir.
Yeah, sure. Thank you. So this is now equal to equal to minus k, and I can take this inside. So what happens inside is basically minus pt, okay, and this x, because this is 1 power of x and this is -1, so you get only minus k plus qt, and because this is okay, so I made a mistake here. So this is, there is no minus sign here, so I'm making a mistake. So that's what it is, and this get cancelled with this thing, so this is what is remaining. And now this I can write it as minus k pt, and x minus k is z plus qt. Okay, so what we get is a linear ODE in z. So more precisely I can write it like this.
Sir, won't the signs be opposite? It will be plus kpt and minus
Yeah,
kqt.
yeah, yeah, right, because I'm taking it inside, and then of course k will multiply here also, and then sure. Thank you. Okay, so I'm making too many calculation mistakes today. Okay, so basically the idea is that we started with a nonlinear ODE, and we end up getting a linear ODE, and then we can solve this. Only important thing to remember is that when you solve for j, so solve for z, and then when you go back, you might get more than one possible choice of solution, and then depending on the appropriate initial condition, you might have to figure this one out. And this you must have seen in the first year when there some examples were discussed. Okay.
Excuse me, sir.
Yes.
So can I explain that step again? X prime equal to minus h x to the power minus x plus k plus 1 x prime.
This one.
Yes.
This is just so this is the derivative,
Yes, sir.
and here this x prime I substitute. I take this one other side, so it becomes minus ptx plus qt x power k plus 1,
Okay,
and
okay,
this is what I have done.
okay, got it.
So I should write here. Yeah, this is already there, and then I just take this one inside. That's all.
Okay, okay. I was actually confused. Like I thought x prime was in the second equation. That's a separate
No,
equation.
no,
Okay, no
there is
problem.
no x prime.
No
That is
problem.
the point. Okay. Okay. So what we are interested in though is not in the. Yes. Hello. Any question? Okay. So what we are actually interested is not in having a method to solve this, because this you already know, and I just present it as an example. What we want to see is that this kind of transformation doesn't always work. Okay. For example, let me discuss another test case. So let's look at another example. And if I look at something like x prime, which is square root of x with the initial condition x0 is equal to 0. Okay. Then I can again use the same transformation, and what I get is Z prime is equal to half. Okay. And then the solution of this, so here you can see that what transformation I used that Z is equal to square root of X. And then once you do that, you get this thing. Okay. Because here K was minus half. Yeah, K was half, right? Sorry, minus half. Yeah. Okay, so now if you do that and then you try to solve this equation, the solution is pretty simple. It's t by 2 and plus some constant, and then you do this, which will be equal to square root of x. Okay, and when you try to go back to x, so this will imply that x is equal to t plus 2 plus c square. Okay, and then you can argue that, well, what will be the c, and then you say that x at 0 is equal to c square. So this implies that c is equal to 0. So your solution will be x is equal to t square by 4. Okay, and this looks a fairly good solution. You can check it satisfies both the equation and the initial condition. But there is another solution which might skip your eyes, but is trivial solution, that if I take x to be 0 function, then it's also a solution. And clearly t square by 4 and 0 are different solutions. Not only that, there is no need to stop here. I can combine this 0 and this t square kind of thing, and I can claim that something like x ct, so this is going to be a parameter family where the parameter sum c is equal to t minus c square for t greater than equal to c and 0 if t less than c. So for any parameter c positive, xct is a solution. Okay, I mean clearly you can see that it satisfies the initial condition. Okay, because c is positive, so solution is 0, and then it's just a question of checking whether it satisfies the ODE or not. Okay, so if you want, you can see that the xc prime, this is nothing but 2 t minus
Sir,
c.
will a half should come,
Yeah,
right?
that's what I'm checking. So if there is a half, I'll put it there. Okay, so let me check it. If there is a constant missing, I'll put it there. Most likely there should be a half. You're right. Okay, so this is equal to yeah.
There should be a 4, I think.
Yeah, let's see. Yeah. Well, for C, yeah, it should be. Let's see. That's why I'm doing the calculation. Maybe there is some mistake here. Okay. So now this should be equal to square root of x. Okay. So let's try to now adjust. So square root of x. So let's, if I put it here 4, so it will be 2 by 4, and this will be basically half t minus c, which will be equal to square root of x. So I need to just change it to 4. Yeah, so this is fine. Okay, so of course note that this t minus c is always positive, so this all these things make sense, because this is only defined for t bigger than c. Okay, so now the idea is that how to get rid of these kind of things, and how to arrive at appropriate conditions, so that we can know in advance that for under what condition this happens and what condition this does not happen. So mind you that if you have this problem to solve, this is the situation you will get. So you cannot, sometimes we cannot change our problem. So in this case, you will have more than one solution. So this problem will not be well posed. So if you can change your model in such a way that you don't get these kind of things, then it's fine. But sometimes it's also not possible. So you might get stuck with this thing, and then you might be interested in only some of the interesting solutions. But mathematically speaking, this need to be avoided. So we want to have appropriate conditions on something so that this kind of things can be excluded from the discussion, because that will not be a fair mathematical discussion. So in that discussion, now we'll start with the nonlinear equation. To be more precisely, we'll not start with the completely nonlinear equation. We'll start with something called semi-linear equation. Okay. So what is semi-linear equation? These equations will be basically form of x prime is equal to f t comma x with the some initial condition given at some x naught at some t naught. Okay, so note that this is not completely nonlinear. Completely nonlinear equation, if you look at what the form of that will be some capital F t x x prime is equal to 0. Okay, with some initial condition. And we don't, in general, what happens is that it becomes harder to discuss existence and uniqueness and the well-posedness of these kind of problems, because in fact even getting expression for x prime out of this nonlinear relation becomes complicated. Sometimes it's actually not even well defined, right? You cannot always open up a function and get the implicit this right in explicit form. You cannot solve this. What I mean by that is you cannot always solve all the equations. Okay, so to avoid that additional difficulty which will come out for writing the expression for x prime, we consider this situation. If you can write from this equation x prime is equal to something, then it's fine, it falls under this category. Otherwise we we cannot say anything about it, because that difficulty is not due to the structure of the equation, structure of the from the ODE part. That is only because of the structure of that particular f, capital F. Because, yes.
Why this is semi-linear equation, not a linear equation like the earlier ones? Because it is like in the earlier examples we can write the second means we can keep the x in one side and the other part on the other side.
Yes, so a semi-linear equation involve, of course, cover the linear equation, like non-linear equation also cover the linear equation. Okay, I mean, in general, when you discuss the nonlinear equation, that can be so. For example, this kind of equation also covers that linear equation part. So linear equations are one test case, but this is much more general. Here I'm allowing it to be an arbitrary function of x. So this will cover that part. You're right. So the analysis of this equation will cover the analysis of the other thing, but this is much more general. Does this answer your question?
Yes, sir, I don't understand the completely means why then we are studying this and what is the extra part in this?
Oh, I don't know where you stuck. So this is not only linear. This can be anything, right? This can be something like t x power 5.
Oh, okay, sir, okay.
You are thinking other way around.
Understood, sir, understood.
You are thinking other way around. I think that is okay. So now what our aim is to, of course, note that now f here is a function from basically some omega to r, and omega is in R2, right? Because f depends on x and t, so the xt basically you will have x comma t or t comma x, whatever way you write. They both are in element of R2. Okay, so now we'll try to understand that how to solve this kind of equation. You already have some theorem, at least one theorem was given to you, if not proved, in the first year, that how to that under what condition these solution exist and unique, and we will actually aim to prove that theorem here more rigorously. So can somebody recall what was the theorem from the first year? Can you recall what was the existence uniqueness theorem for the first order ODE? Remember something called Lipschitz continuous? And that was the only difficult question, right, in ODE. So the aim was basically, if you have something like this f happens to be Lipschitz continuous in the second variable, then we can basically claim that the solution will exist and it's unique. So we will try to make it very rigorous, and we'll go through the proof of this concept in a purely detailed way. Okay. Now, before that, let us try to understand how to solve these kind of things. Okay. So, and what is the philosophy, how we go about solving these kind of things. So the main idea, what we do is the following. Always we try to convert differential equation into integral equation. Now, this might look like just a mathematical trick, but actually, if you look at and if you develop a certain amount of understanding for the differential equation, you will realize that this is actually the way ODEs are derived fundamentally from observation. Okay. So what I mean by that is the following. Let's take this thing and integrate it. I don't know the integration as such, but let's assume that you can integrate it. So what you get? So you get integration of x prime dt is equal to f t x, of course will be some function of t dt. Okay, this will be, if I integrate from t naught to t, this implies that x at t will be x at t naught plus t naught t f t comma xt. So let's not write t here, let's write s here, because otherwise the limits and the variable of integration will be same. So let's write s ds. So note that if f is a continuous function, then the ODE, let's call it 1, and this let's call it 2. 1 and 2 are equivalent. That means x will be a function of 1, x will be solution of 1 if and only if it's satisfied 2. Okay, because if f is continuous, that means by fundamental theorem of calculus, this integral will be differentiable. So I can take the derivative of xt here in the second equation. When I take the derivative of this equation, then this will disappear, and then what will be left is the just ft comma xt by fundamental theorem of calculus. Okay, so these 1 and 2 are equivalent statement, and note that here you trying to look at it is that the change in x at time t is given by this function. Here what you see that change in x from time t0 to t is this integral. Okay, and under appropriate condition on this function f, for example continuous, these two statements are equivalent. But what is the mathematical difference between them? The mathematical difference between them is that, note that the second equation need f to be only integrable. If f happens to be an integrable function, and when you open it, so this whole thing happens to be integrable function, then this integration is well defined. Okay, and then once this integration is well defined, then this is well defined. So ideally you just need to be this to be integrable. Here you need x to be differentiable by the definition of the derivative. Here there is no derivative of x involved, so even if x happens to be continuous function, f happens to be continuous function, this is whole thing will be continuous function. So this is still fine. So the 2 makes sense. So 2 is much more general situation than 1. And in most cases, of course, when 1 makes sense, it will be equivalent of 2. Okay. So we will not solve this, we will solve this. So let's write this integral equation. So the equivalent integral equation will be basically xt is equal to x naught plus integral t naught to t f s x of s ds. And this you can see is basically a implicit integral equation, right? So it's a implicit equation. And why it's implicit? Because x is also here and here. So now the question comes how to solve this thing. As you can see, I will never discuss this thing, because once I have the solution for this, by fundamental theorem of calculus, x will be differentiable, and then I can say that this is automatically satisfied. Okay, of course I need to give the appropriate condition on f for this to be true. So our aim will be to understand the solution of this equation. Any question so far about this?
Sir, I have a question that
Yes.
the second and the first equations you said are equivalent when f is derivable.
F is continuous.
But sir, the first equation needs f to be derivable.
No, it needs x to be differentiable,
X
not
to,
f.
right.
Sir,
Yes.
so once could you explain the conditions when 1 and 2 are equivalent?
So if f is continuous, then they are equivalent.
So f should be continuous in both variables.
Yeah, of course. When I say f is continuous, it is continuous in both in t and x. Yes. Note that if f happens to be continuous, it automatically implies that x prime is also continuous. Okay. All right. So if there is no other question, we proceed and we'll try to analyze how we will solve this equation. Now, can somebody give me some ideas how to solve this equation? Note that this involve the solution of this equation will be a function, okay, function xt, and the dependence is a little bit tricky in a way that x at time t depend on all the values of x up to time t. So it's a kind of a implicit dependence. Now the way to solve these kind of things is something called fixed point method. Now this is not the fixed point method what you have seen in the first year calculus course. You recall that if you had a equation something like x is equal to phi of x, where let's not write x because that will confuse you. So let's write, if you have to solve t equal to phi of t, then you had some appropriate condition on phi, right? If phi maps ab to ab, and if phi prime is less than 1, then there exists unique fixed point of phi in AB, and fixed point here means that T star is equal to phi T star. So that will solve the problem, and these were the conditions. So you can do something like that here, but for that you need a little bit more topological structure, because all these things has to make sense, and you see the domain here will be something else, because these are not real values, these are functions, and then you need to appropriately change the norm, and you can do exactly the same thing, because this fixed point theorem also holds in some complicated Banach spaces also. If you don't know what is Banach space, they are complicated vector spaces, but we won't do it, we just take some idea about it. And we recall what was the fixed point iteration. The fixed point iteration for to solve this is that you can take any T naught in AB, and then you recall that you define this Tk is equal to phi Tk minus 1, and this will always converge to T star if these two conditions are satisfied. Now we'll do something like this. So we'll take the approximation idea. We'll take this idea, not this theorem idea. We'll take this idea and we'll try to see under what condition this apply to our case. More precisely, what we'll do is the following. We'll define a sequence of function. Okay, x naught, and then x1 or xkt will be equal to, one second, equal to x0 plus t naught to t f s x k minus 1 s ds.
मैंने अपने उससे किया
Okay, so now you can see that this is a iterative process. Okay, so this is a iterative update, and these are called Picard's iteration. Now what is our aim? Our aim is to show that this sequence of function converges to a continuous function let's say xt. Okay, let's say it's converges to xt. We have to show, we have to define what is xt, and we have to show that it converges to xt. That's a different discussion, but our aim is to show basically that it converges to a function xt, and of course we have to define what is this convergence means. Okay, furthermore we want that x satisfies such that, because showing convergence has no meaning if it doesn't solve our ODE. So such that we want x to satisfy this equation. Okay, so this is our aim. These two are our aim, that we need to identify what is x, and then we need to show that x satisfy this condition.
What's the first condition?
No, there is only one integral equation. We need to show that xt, the function which we identify, satisfy this integral equation. Okay, of course we still have to define what is xt. Now to do that, there are several important questions are there. Now, if you assume that xkt converges to xt, to show that this integral equation is satisfied, what we need is to look at this iterative method, look at this Picard's iteration, and let me write this Picard iteration here once more. So here I am trying to just put things together to show you what are the things we need to study. Okay, so let's look at this Picard's iteration and let's take the limit k tending to infinity both sides. Okay, now this is equal to x naught plus, if I can take this limit inside, then it's fine, because f is a continuous function, then xk converges to xk minus 1 converges to xt, so life is easy. So I can write it integral limit f s xk minus 1 s ds t naught to t, and this will give me x naught. So assuming this limit exists, this will give me xt this side, this will be something like f s x s ds. So what this involves, the most critical point here is that we need to switch this limit k tends to infinity and the integral. Now please note that the integral of a function is also a limiting operation, right? What do you mean by the integration of a function? Integration, you did this Dolbeck sums, right? You did this upper sum and lower sum and then took the limits, if you recall. So here what you're trying to do is that you are trying to commute two limiting operations. So first, in this case, you are here, you had direct sum, so you had upper sum and lower sum limit, and this other limit is basically k going to infinity. And now you want to change their order. You first want to take k to infinity and then take this upper sum and lower sum things. So this is a very famous question in mathematics, and it's very important in many situations, is that when can we switch limit and integration? Of course, it's nothing specific about limit. Integration, it can be asked about the derivative also, when we can switch derivative and the limit. Okay, but most important, so the most application point of view, integration is more important. So we can generalize this question and we ask, let's assume, okay, so now first thing, please let's keep the full picture in mind. We need two things. One is this thing. We still need to find what is x, and second is that we need x to satisfy this, which we will try to do it via this way, which will involve the switching of the integral and the limit. Now first I will discuss the second part, that under what condition you can do this. Please note that we need appropriate condition. We cannot just for any functions we can do it, and I will explain you what exactly the condition we need for that. Okay, so please understand the mathematical difficulty here, that this is not trivial. And this is of course not trivial. So these are the two critical parts involved to find solution of this ODE, which we converted into integral equation. Okay. So now the question is, the mathematical question what we are trying to see is that, assume, let's take a function h and t, and it converges pointwise. I will explain you what is pointwise to ht. Pointwise means that is for every fixed t, you fix the t, hn will become a sequence of numbers, and this will converge to h of t. Okay, so deep down, what is the difference? Deep down difference is that if you recall what is the definition of convergence of sequence, h and t minus ht is less than epsilon for all n bigger than some capital N. Here this capital N will depend on this t because you have fixed that. Okay, so this capital N depends on the t, and this is called pointwise convergence. Is this issue clear? Is this thing clear to you, what I'm saying?
H of t here?
Sorry?
H of t. What is it? Any random function?
No, this is a function to which h and t converges. And I am defining ht in such a way that for every t, if you fix a t, so hn becomes a sequence of numbers, right?
Yes, sir. Got it.
And then that sequence will converge to that number ht. ht is a fixed number because t is fixed. And note that because t is fixed, this is called pointwise convergence, by the way. Because t is fixed, this n, capital N, which you should remember from the definition of convergence of sequence, will depend on this t. And this creates most of the issue in our analysis. This dependence on t creates most of the issue in our analysis, which we'll see in a little. But here I just want to show you that if this is the case, then the limit n tending to infinity integral h and t dt, or h and let's write s ds over some interval need not be equal to limit of need not be equal to hs ds over the same interval. So we observe that h and t converge to ht for at every point, but still of course, and this if you note that this is equal to integral I limit n tending to infinity h and s ds, right? So we observe that in this case we will give a counter example to show you that you cannot change the limit and the integral sign. They do not commute in this case. Okay, so this simple notion of convergence, what I have shown you, does not allow you to exchange the limit and the integral. Let's look at a very nice example. This will help you clarify many things. Okay, so I will just draw the picture, and from the picture things will be clear. And of course, then you can write down the expressions later. Let's take this is t-axis, and I will define what is h1t. So h1t basically will lie between -1 and 1, and it's a hat function, something like this. So these are straight lines. Let me draw them with a little bit more straighter. Okay, so these are straight lines, and they are in such a way that the total area under this thing is 1. So so the integral of h1t is equal to 1. Okay. Now I will modify this h1t to get h2t. My h2t will be minus, so this will be minus half. This will be half. And here I will increase the height. Okay, such that the area is still 1. Okay, and I can keep doing it. And of course, now once I gave you all these expressions, all these condition on this function h, you can easily find out the value of what is this function hx, hnx. Okay, so for nth function, I will still have their integral to be 1. But they will be non-zero only from minus 1 upon n to 1 upon n. So you can see that the base of the function is decreasing and the height of the function is increasing, right? So the area where the function takes non-zero value is decreasing and it's basically going to the value, singular value 0, and height of the function is increasing, so the top value will go to infinity, right? You have to compensate accordingly. So now note that pointwise for all t not equal to 0, h and t converges to 0. Agree? Is this thing clear?
Yes, sir.
Okay. So and note that if you look at the value t equal to 0, h and t is going to infinity. Okay, so ht is a function which basically is infinity at t equal to 0 and 0 at t not equal to 0. Okay, so this is a famous Dirac delta function what I am constructing. So now note that what we should do. An important thing what you should also observe is that the limit over whole R of h and t dt is going to be equal to 1. For each n it's 1, so its limit will also be 1 because it's a constant sequence. On the other hand, if you look at the function like this, okay, I'm just observing the function like this, then the integral of h of t dt, this either will not make sense because the function is unbounded at 0, or if you remove this singularity at 0, this will be equal to 0 because it's a 0 function, right? And the point value at a point does not make a difference in the integral. Okay, so what do you see? You see that the integral hn s ds or r limit n tend to infinity is equal to 1, but the integral over r of h t dt is 0 or not defined, which whatever you want to take. Okay, so this equality will not hold in this case. So what we need is a stronger notion of the convergence. Pointwise convergence is not enough to change the limit and the integral. And in the next class, we will discuss this stronger notion of the convergence. What we need to do here is that we need to make this n independent of this t. If we can do that, then now we will prove that this equality holds. Okay, so this is what we will discuss in the class on Tuesday. So I hope that at least the problems are clear. What problems we need to address? We need to allow us to change these limits. This is the first problem I'm trying to address, although it's numbered as 2. And the second one is identifying this x and show that this converges appropriately to this thing. So that's why this convergence is also question mark. Okay. So with this, I stop for today. And if you have a question, I'm here and please ask the question. I'll upload these PDF of these notes what I've written here to you today itself. I did not do it for the last class, but both of them will be done today. Okay, so I'll stop the recording and then I'm here.